So far, we've seen how to arrive at this algorithm that we just talked about before, and we concluded that for Q-learning and deterministic policy gradient, we won't need to make use of important sampling. What we're going to talk about now is compatible function approximation. Basically, like we talked about before for the stochastic case, similarly in the deterministic case, we can find a critic such that the gradient, the actual gradient of the Q-value function, can be replaced by the gradient of this approximative function. And if we can replace it like that, it's called compatible for the sake of the algorithm. So you will get the same result as if you actually had the Q function available. The specific criteria, we won't list those for when this is applicable. They can be found in the paper, but generally there is, under some reasonable conditions on various input functions, this sort of relationship exists. And for any deterministic policy in particular, there always exists a compatible function approximator of the form that we can see at the bottom. So on the right-hand side of this, like on the very right-hand side, we can see a v function that only depends on s, and that is interpreted as the value of the state s. So remember, the Q value, or the Q function, indicates basically the action value. So the value of being in a particular state and taking a specific action. Now, this v of s indicates the value of the state itself. And then the first term here, which can be summarized as a of s and a, so a of the state in action, is the advantage of performing action A compared to what the policy would otherwise generate. So this is a deterministic policy whilst being a state S. So if we imagine following the deterministic policy, then the advantage would be 0. So this would collapse to only be v of s, and in that case, that would be the value of the state. And that makes sense, because if we have this state action value function, that would simply be the value of that state if we act according to the policy, because what the value of the state should represent is exactly that, what we expect if we're following the policy. So we have those two functions, and then using that, we can derive a compatible off-policy deterministic actor-critic Q-learning algorithm. The critic then would be a linear function approximator that estimates the action value from a set of features, and we can recognize this from the previous slide here in the bottom. And we should note that this is a linear function approximator, and in general, it's not useful for global prediction of the action values. So imagine having a Q function that's very distorted, or even if it's not very distorted. The thing about this is if we're doing a linear approximation, it's going to tend to infinity in the bounds, right? So you could imagine this in 2 dimensions for simplicity. If you have a simple XY graph and you put a line through that graph, eventually it's going to tend to positive infinity and negative infinity, so long as the slope is not identically 0. And the same thing then would be a problem in the case of global prediction for the action values. However, this is not necessarily a problem, because what we're using this sort of approximation for is in the algorithm where we're updating our parameters. And so if we do a linear approximation of this Q value function, we're going to have a good representation, so long as it's reasonably smooth, the Q function. So that's something we need to assume. But provided it is that, what this represents is the local advantage of deviating from the deterministic policy that we set for ourselves, and then locally improving our policy parameters is then possible using this function approximator, because we see, at least in a greedy sense, how we're improving based on small updates to the parameters. So the critic is a linear function approximator, and it serves well for the purposes that we're intending. And it's learned off policy then from the sample of a behavioral policy, beta. And this can be done in a number of ways, but for this particular algorithm that we're considering, it's Q-learning. And then the actor updates parameters along the critic's action value gradient. So similar to before, we have an expression then for this algorithm down here, and we have the policy parameters, the Q function parameters, and then lastly, the state value parameters. So we showed in the previous slide basically v of s, so that would be the value of state s, and then we also had the deviation from that value given a certain action. So yeah, that's what's new basically for this algorithm, the updates to the v-value function. But otherwise, this is a Q-learning algorithm that takes into account an off-policy deterministic actor critic. So that's pretty much it. And next, there are some applications and scenarios where this is applied.